All right, here we are with part two of the chapter one notes. So I know it says part two there, and I suppose that's coincidence. So here we go. And if you see me looking to the side, it's because I have a second screen, and that's where my camera is, or where my video is. So just want to let you know that. But anyways, the next set of questions, the next style of question is I'm going to ask you the type of sampling you see being used. So sampling is the process of using chance to select individuals from a population to be included in the sample. If convenience is used to obtain a sample, the results of the survey are meaningless. So basically, we need everything to be random as possible. So we're going to skip this example. Much of these notes talk about how to take these random samples, but it's not something that we're going to do in the homework. It's not something that we're going to do on Canvas. So I'm not ultra concerned with how to do this. There's a whole bunch of computer programs that can set this up for you. I want to be able to identify which type of sampling method we're using. So the first one is simple random sampling. And there's not really a definition listed here, so I want to just clarify above it. So definition. A simple random sample. A simple random sample also known as an SRS, is a sample in which any group of size n, of size little n, is equally likely to get chosen. To be chosen. Which any group of size n is equally likely to be chosen. So this is kind of like a lottery. I know many of us don't play the lottery, but if you've seen it in TV shows or things like that, it's basically a big gumball machine, spits out more or less ping pong balls, and each one has a number. And in theory, every group of 5 or 6 numbers, however many is being chosen, are equally likely to be chosen. So what's weird about that is 1, 2, 3, 4, 5 is just as likely as any random group of your favorite numbers that you might have filled out on your lotto ticket. So if there's no organization, it's just purely random. It is a simple random sample. So it shows the steps here. This is not something I want us to really latch onto or highlight or memorize these steps, but let's just read them through real quick. Obtain a frame that lists all the individuals in the population of interest. Number these individuals. Then use a random number table, graphing calculator, or software to randomly generate your desired sample. So this is all very complicated language, but just as examples of what this looks like in real life. So again, let's cross this out and we'll say real life SRS examples. Oh, my screen just went black, so give me a second here. Oh, cool. Real life SRS examples. The kind of old school, non-technological way would be names out of a hat. You might have done this as a kid to pick random teams or random groups with your group of friends or like your cousins or whatever. You might have done this. This was technically a simple random sample. Popsicles out of a jar, however, whatever version of this you did. A different way you can do this that's a little bit more formal, because the second you're trying to pick 100 students from a campus or 1,000 students, this gets ridiculous. It would be a random number generator. Random number generator. So those are the two ways we're really thinking about it. If the method described seems very similar to either a random number generator or names out of a hat, it is a simple random sample. And a random number generator operates under the presumption that we've all been numbered. But we really all have. When you think about it, there are a lot of numbers that are assigned to you. As scary or weird as that may sound, it's true. Think about it. We got driver's licenses, hopefully, or some of us. We have passport numbers, some of us. We all have social security numbers, or maybe not all. School IDs. What else? Phone numbers. All these things that are assigned to us, we can put in a program and randomly generate 5 of those numbers, 6 of those numbers, and then create a random number generator. And programs are smart enough now to where we can just give the names and they will randomly create a group of however many. So if you use a computer, that's what's happening. In the coding, it is giving each situation a number and choosing random numbers, or just old school names out of hat. So that's one way. So just to keep perspective of what's about to happen, we're creating a style of question to where you'll read the situation and then you'll pick from the different types of sampling. Our first sample, what we just talked about, simple random sample. So we skip that example. Okay, so the next one, we now look at various types of sampling techniques. Most of them have some sense of randomness. Even if it's not perfectly random, it might be designed random or maybe a little conveniently random, but we do the best we can. A stratified sample is obtained by separating the population into non-overlapping groups called strata. That's kind of old school language. You might have heard that in like biology, but anyways, old school group or in non-overlapping groups called strata, and then obtaining a simple random sample from each stratum, plural of strata. The individuals within each stratum should be homogeneous or similar in some way. But notice, we then take a simple random sample. So it is random in some way. So what I like to write down real quick are some common strata that people are split up into. And I don't want to give too many away because this might be a future discussion that we talk about. But some common strata that we might break people up into are race and ethnicity. So depending on the situation, we might want an opinion or some data drawn from each race. To where if we just did a simple random sample, we might exclude certain races depending on what state you're in or where you live. And we might need the opinion of each race and ethnicity. So that's something we want to make sure we do. It's something that is often stratified is race and ethnicity. And another one that goes alongside that, I'll give you a second to think, gender or sex. Same thing, depending on your situation, it's totally possible to randomly get way more of one gender or one sex than you would have naturally. So if we just make sure to obtain a certain amount from each gender or each sex, then we might get a more honest opinion or an honest representation of the population. And that's our goal when sampling. So that's that there. So I'm just going to leave those two. There are a ton more. These are very, very serious strata and very important strata, but it doesn't have to be that serious. The population, you can split the population into different stratum in a whole bunch of different ways. That may even seem kind of silly sometimes. So the example here, a sample of 100 undergraduate San Jose State students is taken by organizing the student's name by classification, freshman, sophomore, junior, senior, and then selecting 25 students from each. So why is this sampling technique stratified? It's because you can't be a freshman and a sophomore. They're non-overlapping groups. And then I took 25 from each. So that's our second style of sampling. The third style is going to be systematic. Sorry to brain fart there. A systematic sample is obtained by selecting every kth individual. When I say kth, I mean, third, 25th, something like that. 12th, second, every other, every 50th, every 100th, things like that. That's what kth means. And the first individual selected is a random number selected between 1 and k. So there's a further way to randomize this. So if you know you want every 25, I randomly select one person from the first 25, and then I go every 25 from there, just to truly randomize the situation. So it's explained there. For more or less, we can ignore these steps. It's not something we need to memorize or pay attention to. But if you're curious, this is the formal way to do this. An example, quality control engineer wants to obtain a systematic sample of 25 bottles. And it says, design a sampling technique that can be used to obtain these bottles. So the point here is that systematic sampling is often used in assembly lines, any sort of manufacturing of food or drinks or snacks or microchips or phones or batteries. They're all tested through systematic sampling. Or I'd imagine maybe not all, but most of them are. So I take every 10th battery and do something like this. So this example is not a quality example for the type of work we're doing. So we're going to skip this. And what we're going to really need to be able to do is just recognize, hey, are they taking every 10th thing? Cool, systematic, right? This is a multiple choice question we're talking about. The next one is a cluster sample. A cluster sample is obtained by selecting all the individuals within a randomly selected collection. So this definition is not so clear. So we can clarify by saying something like this. Entire groups are randomly chosen. Entire groups are randomly chosen. So that might clear up the definition. So the first three we talked about, simple random sample, stratified sampling, as well as systematic sampling, are the most ideal styles of sampling, but they're not always possible. Think about humans. We're not always lined up in a line. If we had a group of people that are just sitting in a quad or sitting in a mall, it'd be very difficult to go collect numbers from all of them or assign numbers to each of them and get a simple random sample. We don't know the stratification of each of them. We can't force them into some sort of group that we need them to be in. And then choosing a simple random sample amongst them would be difficult. So if we still want to be random, but don't want to be overwhelmed by the amount of work we have to do, cluster sampling is a good way to do things. So if you notice your classroom, you're naturally in clusters, in rows. Let's say you have 5 rows in your classroom, and then I randomly choose 2 of those rows. So there's still a sense of randomness. Maybe it's not perfectly random, but it's the best we can do with the resources we have at that time. So it says here, a school administrator wants to obtain a sample of students to conduct a survey. How can the school administrator use cluster sampling? So I'll let you think about this just for a second here, but you can see how if I needed to ask 100 students a question, it would be really annoying to use a simple random sample. Because I have all your IDs. I can choose 100 different ID numbers. Tracking all 100 of you down is going to be ridiculous. You're not going to respond to emails. Some of you are going to be absent. Some of you just might refuse to answer, or there's a whole bunch of situations. It would be annoying to track you down. And you're going to be in different places at different times of the day. So what I can do is randomly choose 6 classrooms in third period. And that might get a good mix of the population of your campus. Right? In third period, people have usually started by then. They've not gotten off early. I'm just trying to think of how my high school went. You know, we didn't have block scheduling, which I know many of your high schools do now. So I'm not always sure. But some of the students at my high school could start late. They had to start by second or third period, and some can leave early, so they can leave after fourth period. So I know the entire school would be in the classroom at third period. But again, your high school might not be like that. So maybe a different period is more ideal for your high school. But anyways, that's one way to do this. So something we want to look or be careful about is stratified and cluster sampling feel kind of close. They both have groups, but here's a clarification. You know, they are different. In a stratified, we divide the population into 2 or more homogeneous groups, then take a sample from all the groups. To whereas the cluster sample has groups, but we randomly choose all the individuals in some groups. So it's very weird. So it might take a second to kind of internalize that. But this is the first one, sum from all groups. And then all from some groups. So they are different. Cool. So hopefully that made sense. The next bit is a convenience sample. A convenience sample is any sample in which individuals are easily obtained. So if you've ever done a project where you need to ask people some sort of question, chances are you personally did convenience sampling. Random sampling is very difficult and kind of annoying to do. So most people tend to resort to convenience sampling. And this is not just you as high school students or as college students. This is everybody. This is every group of people, news outlets that are trying to do sampling. They tend toward this convenient sampling because it's in the name. It's convenient. It's easier. Should they do this? Absolutely not. But it is what happens, unfortunately. And look at this warning. Any studies that use this type of sampling generally have results that are suspect. Results should be looked upon with extreme skepticism. So if you've ever come across anything on Instagram or Twitter or BuzzFeed or some random polling and been like, there's no way. I'd put money that there was a convenient sample somewhere in the background. So, yeah, something to watch out for, something to think about. We want to be more informed people. We want to be a little bit skeptic or a little bit critical of what we read online. So, anyways, in practice, that it says here, most large-scale surveys obtain samples using a combination of the techniques. So hopefully there's some sense of randomness. This example I also don't like, so we're going to skip this. So like I said, we saw 5 sampling techniques. You're going to see in the homework, it'll give you a situation. and you'll read it through and you'll have to choose from one of these five. And this is what the quiz and test is also going to look like. Hey, what sampling technique was used? Simple random, stratified, cluster, um, or convenience. Feel like I missed one. Or systematic. Maybe I missed that one. But anyways, you get 5 options there. Cool. So earlier in the notes, or actually in the first video, we split up quantitative into 2 styles of quantitative variables, continuous and discrete. Qualitative has a sense of a breakdown also, but it's a little bit confusing, and we'd spend a lot of time here trying to distinguish between them, and it's just not worth our time. It's not that valuable the thing to do. It's not something that's that notable or usable in real life stats. So I personally don't go over this in my course. So this whole page is out. These notes that are given to you are a little bit standardized from other instructors that have taught this dual enrollment course. So I'm going based on their notes, but we're still going to be the most efficient with our time. Let's say that. Cool. So moving forward, back to graphs, really. So the first step in summarizing quantitative data is to determine whether data are discrete or continuous. And 1 second here. For building a frequency distribution, because we're going to do that, again, the same, very similar to how we did earlier. We're building a frequency distribution. If the data is discrete and there are relatively few different values, so you can see in this little data set here, there's only 0, 1, 2, 3, or 4. The category of data will be the values, as in the qualitative data. So there will be the values. So just like earlier, we had red, blue, green, brown, yellow. This one, there's going to be 0, 1, 2, 3, 4, 5. But if there are many different values of the variables, or if the data is continuous, the categories of data, the classes, must be created using groups of numbers. Group, or the classes. These are what we call classes. Groups of numbers. This is the harder scenario. Neither is really that hard. There's a good chance you actually went over this last semester. So we look at this. We could organize this in a frequency distribution that looks like this. So we're talking about the number of cars. So over here, you'd put number of cars. And then frequency. And of course, on a test, there's a good chance you would also include relative frequency in this third column. And since there are a few different types of values, we would just do this 0, 1, 2, 3, 4, and I do see a 5. But for some practice, I think it would be useful to start practicing some techniques here. And I'd like you to enter all of this in one of your lists in the calculator. So the chance you saw this in the first video and have practiced this, but in case you forgot, you're going to click Stat, then Edit, and choose a list and enter. So I'm going to flip the camera, stop the share real fast. So what we're going to do is click Stat, and then click the first button, edit. I put my data in L2, so I think it's a good idea if you do that as well. So go ahead and press pause and try this with the data. Alrighty, so hopefully you've entered that now. And I want to show us a couple things here. And these aren't vital things at this moment, but I think they're very helpful. So now, I'd hopefully want to count the number of all these. So I'm going to click stat, sort. So instead of going edit, which we've done in the past, we're going to click sort. Then it's going to ask me, hey, what do you want to sort? And then my data is in L2. Your data might be in L1. I'll click second. And then 2 to get the L2. Click enter. And it's like, cool, I'm done. So now I go back to the data and you can see it's all entered there. And I can now count it 1, 2, 3, 4, so on and so forth. But I want to kind of get ahead of the notes. This is something that we're going to do later in the course and create a chart called a histogram, which is basically a bar chart. So the way we do that, second y equals, because I want to get to the plots, stat plot. So we're going to go second y equals. Make sure everything's off. And I'm going to click on 1. The first one's on, and that's okay. So don't do that. I did that on purpose. But go to plot 1, click on this. You will likely be naturally clicked on this first graph. You're going to click over to the third one, where it is, it looks like a bar chart. It's actually a histogram. We'll click on that. Choose the list wherever your data is. So mine's in L2. And then we'd click graph. Many of us are going to get syntax errors. There's a whole bunch of different reasons for this. You're going to have to work together to kind of figure it out. The most common reason is that in your backpack, if you click just y equals, don't click second, just y equals. Well, I guess quit first. Just y equals. You have a bunch of random crap here. So make sure it's completely clear and click delete right there. Or clear. Okay, now go to graph. And then for most of us, or many of us, you're going to see a big old blank. Big problem. So basically, it is showing you the place where you last saw your graph or you last had your data. So I have new data, so my graph isn't there. So what you're going to want to click is zoom and then number 9. Now you can see some sense of data. But this is not perfect data, right? This isn't a perfect bar chart or what we'd call a histogram, because I don't know how the numbers are grouped. But next up, I know this is a lot, so you can always press pause, rewind, and write down these notes. We're going to click window. And the thing in window we really want to focus on is X scale. And X scale is the size of your rectangles, the size of your classes. So I'm going to click 1 because my data goes up by 1s. And the X min is the most left I can see. So I'm actually going to click -1. I know I don't have any data in -1, but just to see where my graph starts. And then click graph. So now I see something, again, that looks like a bar chart. It's not a bar chart, it's called a histogram. But the next step is click trace. So from 0 to -1, which is all my zeros, I have 4 of them. And then I have 13 ones. I have 22 twos. 7 threes, 4, 3 fours, and 1 5. If you entered your data correctly. So that's just one way to make your life a little bit easier. So I'm going to switch back to the notes and switch back to the forward-facing camera. One second here. So we just looked at this in our calculator. Hopefully you were able to catch all that. But bottom line is the frequency is 4, then 13, then 22, 7, 3, and 1. And then I can plug all this into my calculator and start dividing by the total. But since there are 50 households here, it's a pretty easy division problem. 4 divided by 50 gives us 0.08. This is 0.26, 0.44, 0.14, 0.06, and then 0.02. But of course, don't be afraid to use your calculator. And as I say this out loud, I'm double checking that everything actually went correctly. And it looks like I got 50 there. So, yeah. Hopefully that made sense. So bottom line is we can do frequency distributions in the same way with quantitative data. So when a data consists of many different discrete data values or consists of continuous data, which we've already said this, we must create classes. And classes, I highlighted this above, are categories into which the data are grouped. Perfect. No problem there. Some vocab terms necessary to create these intervals. All right, so we have the lower class limit. Lower class limit, which is the smallest data that can be in a class. The upper class limit, which of course is the biggest data value that can be in a class. And then we have the class width, which is how big our classes are. So before we start using these classes, let's just make sure this makes sense. So I look at this and we have some data for ages 25 to 65. And I look at the third class, and this should definitely say 54. That's a mistake in the notes. That should say 54. What's the lower class limit of class 3? Hopefully, we all nailed that, 45. Upper class limit of class 4, the fourth class, 64. No problem. What's the class width? So I'm pausing here so we can all answer this question. But I'm sure most of us are saying 9. And that is a completely fair answer. Most of us are saying 9. Because 34 minus 25, 9. No problem. 44 minus 35, 9. No problem. But most stats books, to remain consistent and for a multitude of different reasons, we want to take the difference between consecutive lower class limits. So the class width is going to be 35 minus 25. 35. Oops. Computer is freezing. Good gracious. Okay. And my pen's not working. This is lovely. I'm going to press pause in the recording to make sure I get my pen working again. All right. Sorry about that. My pen, that took like 5 minutes to fix. But anyways, so it'd be the difference between lower class limits. So the difference between 45 and 35 would be your class width. 45 minus 35. So that is that there. 45 minus 35, which is 10. So your true class width here is 10. And that makes sense for a couple different reasons. The main reason is that count out the numbers in your class. There's actually 10 numbers. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. There are 10 numbers there, even though if you subtract them, it only comes out to 9. So yeah, so what we've discovered is the class width is the difference Oh, actually, sorry about this. This is talking about a completely different style of problem that I actually don't like, and it's overcomplicated, but it's about choosing the number of classes. So, uh, yeah, it gives you specific rules. Something I do like actually is that there should be between 5 and 20 classes, just something to think about. We shouldn't have, 30 classes, 40 classes. It just doesn't make sense. Your graphs are ugly. It's a lot of extra work. Doesn't work out the way you want it to. So if I were to look at this, and we're not going to actually do this problem, but if I were to create the classes real quick. So let's just say the classes. If I wanted 7 classes, I look at this. I want to first identify what is my lowest and highest number. So I look at this and I'm like, hey, my lowest number is 678 that I can see. There might be one I'm missing. And the highest number is 738. And of course, the easy way to check this is enter them all real quick in your calculator and sort them ascending. Very easy to find your lowest and highest. So that's about 80 numbers. So I'm thinking about this. Maybe if I start at 675, what number should I go up by? 80 numbers. I want 7 classes divided by 7. Man, I get somewhere around 11-ish. So I pick a nice, neat number and I go with 15. So I'd go 675. The next lower class limit would be 690. So this has got to go to 689. Then I go 15 again, 705, 720. Oh, and I've mathed this a little bit incorrect, but that's okay. 735, 750. 1, 2, 3. That's 6 classes. So I did a little bit of mental math wrong, and that's all right. 704, 719, 734, 749, and 765. Oops, 764. And that'll cover all my data. And then I can create the frequency here. I don't feel as though we need to waste our time with this. I feel like this is something that we understand. So we'll move past this. And of course, if there's anything that's not clear here, please let me know. Send me an email. Awesome. Okay. We are winding down here. We got a couple more ideas, but in research, we wish to determine how varying the amount of explanatory variable affects the value of the response variable. So it could be the amount of water affects the amount of growth. Let's say we're talking plants, right? The water amount is explanatory. The growth amount of the plant is the response, right? So an explanatory variable is recognized by the researcher and induces a response from the subjects. In algebra, we usually refer to this as X and Y. And in chapter 12, which we'll go out of order, we'll do in week 3, we'll really use this, the X and Y variables. But just real quick, we're going to look at this and say, hey, what is the explanatory and response variable? So I'd press pause and go ahead and read through each of these examples. I'll press pause as well and then post the answers in a second here. So hopefully you read through each of these and figured out that there were two very different styles of experiments slash studies, but they both had the same explanatory and response variable. The explanatory was cell phone radiation or frequency. And then the response variable was tumors, cancer, tumor slash cancer. And so the goal of the research was to say if cell phones cause cancer. Which I know sounds very weird to us as younger people, or I guess to you as younger people, but back in the 90s when cell phones were first coming around, this was a very, very real thing. People felt like it was putting a microwave to your ear because people didn't understand what was happening. So it was a very real fear. But now we're not so concerned. When you read through this, it says there's no statistically significant increase in any tumor type, including brain, liver, lung, or kidney, compared to the control group. So we're not too worried about. But like I said, each of these were very, very different styles of exploration of this topic. The one style, I'm not saying which is which, was an observational study. Observational study. Measures the value of the response variable without attempting to influence the value or either the response or explanatory variables. So this is the key word, without attempting to influence the value of either. That is an observational study. The researcher just watches without manipulating, without getting ultra involved. Whereas if you intentionally change the value of the explanatory variable, if you impose this treatment upon someone else, it is an experiment. So reading these, which one is which? And most books you might actually see random experiment. So I'll say that here, random experiment. Whoa. Experiment. There we go. Okay. So you look at this, and here, these people, this first one with the Danish cell phone users, hopefully we've identified that this is an observational study. Observational study. Because we did not force them to have cell phones. We did not say, hey, you use a cell phone for 21 years. You're never allowed to touch a cell phone. Let's see how you're doing cancer-wise. No, they were already either using it or not using it in the past. And then we just asked them some questions or looked at some medical records and see how they were doing. Towards this one, I imposed radiation. I did something to the subjects, to the experimental units. So this one was definitely an experiment. This is another style of question that I would ask you. Experiment or observational study. So something to think about. So yeah, let's further talk about the differences between these two, because many news reports and reports on social media or media in general will talk about these studies, and they'll not specifically mention, was it observational study or was it an experiment? Or they'll treat them as if they can have the same style of results, but they simply can't. But anyways, let's explore this. Confounding. The big issue with observational studies that doesn't typically happen with experiments, although it can, is confounding. Confounding in a study occurs when the effects of two or more explanatory variables are not separated. Therefore, any relation that exists between an explanatory variable and the response variable is due to something else. A lurking variable is the variable that we didn't think about. So confounding is the idea that something else exists. That specific thing that does exist is the lurking variable. So it's something that was not considered, but the effects of the response variable, but it does affect the response variable. So for example, so we're going to read that in a second, but I just want to talk about a study out loud. There's a lot of studies that have been done about smoking cigarettes, right? And the studies say, hey, the more people that smoke cigarettes, the more likely they have a chance of having a heart attack. And like, cool. The data says that. You look at how much they smoke, the more cigarettes people smoke, the more heart attacks happen. So smoking must cause cigarettes, or I'm sorry, smoking must cause heart attacks. But we have to consider some lurking variables. I did not force these people to smoke. This was an observational study. So they happen to already be smoking. So, what else do we know about people that tend to smoke cigarettes? First off, there's more males. For whatever reason, men smoke more often than females. And it is an established fact that men get heart attacks more often than females. So, is it the smoking causing the heart attacks, or is it the gender or sex? Another thing is, if you're smoking cigarettes, there's a good chance you're drinking a lot alcohol. So is it alcohol causing heart attacks, or is it the cigarettes? So these groups that we've separated in smokers and non-smokers are different in other ways. So it's something we have to be careful for, or be careful with. Confounding just as becoming, future voters and future humans in our statistical society, we need to think about confounding. This will be a discussion topic, I think, in week 3, maybe week 2. But we'll explore it more then. But a good example here. We want to determine the long-term benefits of the influenza vaccine on seniors aged 65 years and older. They looked at 36,000 seniors for 10 years. There were 2 groups. Group 1 chose to get the flu shot. Group 2 did not choose. And after observing these seniors for 10 years, it was determined that seniors who get the flu shots are 27% less likely to be hospitalized and 48% less likely to die. Those are big percentages. So, does the flu vaccination work? I mean, look at those numbers. It feels as though, on the surface level, news reports from certain news outlets might say the flu shot works. We all must get the flu shot. They might be right, but we can't be for sure because, again, this was not a controlled experiment. This was an observational study. We did not force these 65-year-old seniors to get the flu shot and then take another group and forbid them to get the flu shot. They were just already doing it. So, what are the differences in people who get the flu shot and don't get the flu shot naturally? What are some lurking variables? So, I'd really like you to press pause and try to think of some things. And I will write some down. I won't press pause here. Two big lurking variables, and these are not the only ones. I'm sure there are a lot that you were able to discover on your own. 2 big lurking variables are lifestyle and social economic standing. Socioeconomic, sorry. Social sounded wrong. Socioeconomic standing. How much money they got. So, although flu shots are all free now, it wasn't always like that, and they're not perceived as free. So, I'm talking about the second one now. People who have more money may have been more inclined to go get that flu shot. To where if you're, living paycheck to paycheck, you're working that dead end job or that 40-hour, 50, 80-hour week job, and you're not getting any breaks, you might not have the time to go get that flu shot. To where if you do have a lot of money, you do have the time. So if you have the time to get a flu shot, you probably have the time to do other things: exercise, eat healthy, cook. To where if you don't, you might not have the time to do those things: eat healthy, cook for yourself. So maybe exercise. I guess that goes with lifestyle. Maybe it's not so much about people getting the flu shot. It's more about access to a flu shot. It's more about what money can get you. So maybe this is a money thing. Maybe this is a rich versus poor thing. Maybe this is has nothing to do with flu shots. Maybe it does. Who knows? All we're doing, confounding and lurking variables, are really just poking holes in a study. Another bit is lifestyle, and in particular, exercise or diet. I should say lifestyle/diet. Exercise, diet, things like that. Again, it also kind of flashes back to money, but if you're not taking care of your body and you don't care about what you put into your body, there's a good chance that you don't care about getting the flu shot, even if it's going to work, right? I also know salads are good for me. I don't eat those. Why would I get the flu shot? Maybe it's something like that. So it could be just the type of people that choose to get the flu shot are the type of people that generally take care of themselves more. Whether it works or not, there is this perceived attitude of it working. So you don't know. So the flu shot might not work. Turns out, a little asterisk here, even after accounting for potential lurking variables, the authors of the study conducted that getting an influenza shot is associated. So they are connected, they are related, is associated with a lower risk of being hospitalized or dying from influenza. So that's confounding. This is a big test one topic. It's something I enjoy talking about a lot, and we will talk about. So it will be a discussion that will further dive into the confounding of some real world studies that are published today. So here's the thing: observational studies do not allow a researcher to claim causation, only association. So I've mentioned before, I've referenced that observational studies are not as good as experiments. But when you look at the news or look at some post by some social media outlets or media outlets, they're not going to say, hey, it was an observational study, or hey, this was an experiment. So be careful with what I'm saying here. They're just going to assume or act as though everything is an experiment. Because experiments allow researchers to claim causation. Since control allows to eliminate lurking variables. Right? I don't have to worry about the healthy eaters, not healthy eaters. I can have some healthy eaters take the flu shot and some healthy eaters not take the flu shot. And then some unhealthy eaters take the flu shot and some unhealthy eaters not take the flu shot. So it's something I have more control over. So an experiment. Oh, give me 1 second here. Apologize, I got mixed up here. But just repeating the same vocab word, an experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables. Any combination of the values of these factors is called a treatment. So if I were to give some people the flu shot, give some people not the flu shot, that is my treatment. Flu shot, yes. Flu shot, no. Or if there were 3 or 4 different styles of flu shots, flu shot A is one treatment, flu shot B is the second treatment, flu shot C is the third treatment, things like that. So just some terminology, getting used to some of the experiments and studies we'll read. The experimental unit We usually call them a subject if they're people, is a person, object, or some other well-defined item upon which a treatment is applied. A control serves as a baseline treatment that can be used to compare to other treatments. So it would be what would happen normally. So if you read that rat study earlier, there was one type of radiation to one rat, a second type of radiation to a second group, and then the third group, there's no radiation. That was the control group. Let's just see what happens without any treatments. That's a little bit harder when it comes to medicine and humans. Humans realize whether they're getting treatments or not. So we have this thing called a placebo. A placebo is an innocuous medication that is a sugar tablet that looks, tastes, and smells like any sort of experimental medication. Right? So the idea is if I were testing some sort of medicine, let's say cholesterol medicine, I'd give one group the cholesterol medicine and the other group a sugar pill. And this is important because your brain is weird. Your brain is stupid, but powerful. You will get better just because you think you're supposed to get better. There's a HIV medicine that they were studying called ratiregravir. Had a placebo, had the real drug. The placebo group showed 27% reduced levels of the virus just because they thought they were getting medicine. The brain tricked themselves into, oh, okay, let's get better. Really, really weird. The drug ended up getting 48% levels of reduced levels of the virus. So it turns out, the drug was more effective, but we have to have this control group to distinguish between them. And that placebo is important because if you're not getting medicine, you can't trick your brain, is the thing. So in order to operate in this way, in order to trick your brain, we need blinding. Blinding refers to non-disclosure of the treatment an experimental unit is receiving. A single blind, which pretty much will always happen, a single blind is when the unit or subject does not know what treatment he or she is receiving, which makes sense. I can't go to a group of people and say, you get the fake stuff, you get the real stuff, because your brain won't be tricked anymore. So we need the single blind. And then a double blind experiment is one in which neither the experimental unit nor the researcher in contact with the experimental unit knows who's receiving what. Because researchers can be biased. And if they're biased or if they have some sort of investing interest in the drug, they might skew results a little bit, whether they mean to or not. But if you're offered a couple $1 million, if your drug works, you might be a little shady. You never know how you act until that bag's on the table. So something to think about. So pretty important stuff. When reading something in real life, things should always be double blinded if they can. It's not always possible. So let's look at an example and label some things here. The English department of Community College is considering adopting an online version of the freshman English course. To compare a new online course to the traditional course, the faculty member randomly spits a section of her course. Half of them go through the traditional way, the other half do the online version. Then they're given a test at the end. Why is it an experiment? Well, you tell me. It's because this teacher imposed the treatment. They decided you have for doing this and you have for doing this. So the teacher decided who's doing what. Why can't this experiment be double blinded? I'm not going to write this out, but it seems obvious. It's because you know whether you're online or in person. You know whether you're online or traditional. Yeah, I can't like trick you into coming to class and be like, oh, you're actually online. You didn't know it. No, you know, there is no blinding involved there. Who are the experimental units? The students. What's the population? The population is going to be the freshman students at the community college. At the community college. The treatments are traditional versus online, traditional versus online. Hopefully that makes sense. What's the response variable? Response variable would be the grade in class. I'll say that's not very clear from the problem there. And then what are some lurking variables? So let's take a second and think about this. So there's quite a few lurking variables here. I'll admit I don't love this problem for lurking variables because many of the lurking variables are the things I'm hoping for, but some of the variables could be, assuming the lecture is the same compared to the new online course compared to the traditional course, can be quiet place to listen to lecture. Some people need to come to this classroom because they don't have the option or because they don't have the luxury of a nice place to study. It could be not so much the style of class, but just the fact that you didn't have to sit in traffic. It could be drive time. It could be scheduling. Traffic is another one that pops up. And a big one can be learning style. Some people are much more interactive learners. Some people are more visual learners, and that's going to be hard in an online course or vice versa. If you're not an interactive learner and you're more of a, sit on your own, this online course would be more your style. So like I said, I don't love this example to find lurking variables, but hopefully you got something that made sense to you. We've got one less example, but we're just going to skip this because this video is getting really long. And then bias, this small page on bias, we're actually going to leave for next week. There's no homework on this. So I'll make a small bias video next week because it's a fun, interesting topic, but not anything we have to worry about testing and quizzing wise. So that's it for chapter 1. These are long lectures. They do get a little bit shorter and more concise starting week 3 probably. But yeah, good luck on homework and make sure to email me if there are any questions. I will see you all next week.